The comma was
Oh, test. Where'd you guys find the test menu?
second math.
Yeah, second math. So as you're putting into your graphing calculator, let's see if I can actually get there. We need to divide this in two pieces. We have negative 2x with a division and a parenthesis. Then we can go ahead and do x second math. That's the test menu. Less than or equal to 2.
I forgot the parentheses.
I'm not sure if you have to put the whole function in parentheses. Did anybody test that out?
You can just do alpha equal. Yeah, no.
I'll do the whole function.
I don't think you did it.
Are the inequalities in the alpha menu? What is it? Alpha y equals? No. Alpha function? No. I don't think it's in the alpha menu, sadly. Second test, and then we have x greater than 2.
Okay. I didn't know how to make it do that. Okay. Or I didn't put parentheses.
I have no idea what zoom I'm in. I don't think I'm in a very good zoom. No, I'm not. Let's do zoom out.
Just do zoom 6 to start.
I did zoom fit. Oh, yeah, I think I did that wrong.
My windows always are way off because of Ken's.
Zoom fit, you can see it, right? It's just like you can't exactly see it super well. But do you guys see the jump at least? Okay, you see the jump at least. Okay. So for the jump at least, now technically, kiddos, you didn't actually need your graphing calculator for this, right?
No. You can graph it.
You can graph it because I have y equals mx plus b for the first one, and I have a parabola for the second one. Now hold on, just really quickly. When we're graphing a function and we have 2, we need to go ahead and make sure we have the 2, right? But how do I graph the line? By hand.
-2. Yeah.
But from where?
0, 0.
The intercept is mx plus b. Yeah, the intercept's going to be 0 for this piece. Here's mx plus b. I'm allowed to graph it because this is on the left of 2, so I'm allowed to graph it 0. I am going to go down 2 over 1. I'm approximating a little bit, but down 2 over 1. I'm going to go again. The reason being is I'm supposed to go all the way up to and including 2. So I'm going to go down 2 and over 1 more time. Down 2, over 1, and we are there. Now, why am I filling in the circle if this one is less than or equal to?
Because you can graph at 2.
Because, yeah, it says or equal to. It includes 2. So I can graph at 2, and I have that. But what am I supposed to do for this parabola? Now, first of all, a lot of you guys are like, well, I don't know how to graph that parabola. Well, you could just try plugging in 2 and seeing what happens. Some of you are like, but it's not supposed to be or equal to 2. Well, that's true. Except it still has to go all the way up to 2, just not at 2. We could try plugging in 3. 3 squared is 9. 9 minus 12 is negative 3 plus 1 is negative 2. So 3 should be at negative 2. I have that. If I do plug into 4 minus 8, negative 4, negative 4 plus 1, negative 3, I'm going to put a hole there. Long story short, I'm going to have a swoopy swoop for my parabola. Now, if you guys want to be super snazzy, you could do, well, you guys tell me, what am I doing right now? Yeah. You could go ahead and complete the square and do 1/2 of negative 4. And then square that, which would be plus 4, minus 4. I'd end up with x minus 2 quantity squared minus 3. I know my intercept is at 2, negative 3. Oh, hey, that's where the hole is at. Anyway, my calculator is covering it right now. I apologize for that. But I was completing the square. Oh, that's right. That's not what this is. I'll use my wireless mouse, but my USB ports are dying. Anyway, it's a fun day. So, coming back. Good thing I can move today. That's good. Okay, so there we go. Long story short, we have a graph, and that wasn't even the point. Well, it kind of is. We were supposed to find the limit. Okay, I was going to ask you a few different questions of this graph. If I was to ask you the limit as x approaches 0, thank you for the shush because I agree. If I was to do the limit as x approaches 3, and then let me ask for the limit. P.S. You should be writing this down. It's a great example. Calc kids might even see something similar right now.
Well, first,
Well,
C is D.
they might be on the other part. A. What is x approaching in A? 0. So A is 0. There you go. So in A, x is approaching 0. Which means, where am I looking on my graph? As x goes to 0. And I'm looking at my y values. So what is my function doing as I come towards 0? It's going towards a height of 0. Remember, we're looking at the y values. So as I think about each of these individual little points, as I think about this point, and this point, and this point, and this point, remember, we're taking x's this point, this point, this point. I'm trying to ask, where is my function going? What height is it approaching? What height is it approaching? Whether or not it's there? 0. Now, what if I was to move on to the next question, and what if I was to ask, okay, what about the limit as x approaches 3? What changes?
The function, like you did with the other.
Yeah, I'm now on the other piece of the function, because 3 is over here on the green, not the red. So as x approaches 3, remember, we're taking little points along the way, coming and figuring out where they are in the function, where they are in the function. Same thing on this side, taking points, figuring out where they are in the function. As I approach from below and from above, guys, what height am I approaching at 3? Negative 2.
Just plug into the.
Getting there. Getting there. It's the culmination of this lesson. Letter C. What's different about me approaching 2?
Those two, they're both function.
Yeah. Some of you are like, what on earth? But just use what we've been doing. If I'm approaching 2 in the x's, okay, then we think about different points as we get closer to 2. Different points as we get closer to 2, coming from above and below. And we have to take those points down to the curve, remember, and figure out what the points are, what the points are. As I come from below 2, aren't I on the red? And what am I approaching as I come on the red? Negative 4, right? As I come on the red? As I come on the red, as I'm coming from below, I'm approaching a height of negative 4, right? But what's going on as I come from above? And each of these points, what am I approaching? Negative 3. So you see the dilemma? As I come from below, I'm on the red and I'm approaching negative 4. As I come from above, I'm on the green, I'm approaching negative 3. Some of you might be able to look at the inequalities and say, hey, I think I can get that without actually going to a graph. But the long story short of it, what is the limit as I approach 2? Does not exist. Why does the limit not exist? Because as you approach from 2 directions from either side, they're approaching different heights. And kind of as JJ said earlier, there's not one limit. Right, JJ? There's not one limit. I was using your wording, you just weren't paying attention to the shout out. There's not one limit. There are 2 different heights. Therefore, since there is a disagreement, I have to say the limit does not exist. Okay? With that, what if I was to show you, not even show you, I want you guys just to graph this function. Use the grapher. I want you guys to go ahead and once you get the graph, I want you to ponder the question. I'm not even going to necessarily sketch it right this second. I want you to ponder what's the limit as x approaches 4 of the function shown up above. You can use your grapher. You don't even need to use your table. I'm going to freeze the screen while I put it in. If I were you guys, I'd be using my alpha y equals as a shortcut. That's not what I wanted.
Wait, is it does not exist?
Because alpha y equals makes it so that you can put a nice pretty fraction in. You are approaching 4. What's going on at 4?
There's a hole.
There's not a hole. There is an asymptote though. If you were to go tracing, 4 is the location of that vertical asymptote. And if you're looking at your function itself, which is this guy, he is going down as you come from below, and he is coming up as you come from above. And JJ, this is kind of like the one that you had a question on. At least as far as what it looks like when you did the graph. And the only way I can answer this question, if I am approaching the vertical asymptote, and if from one side it's going down, and if from the other side it's going up, it meaning the function, the only way to describe this answer is to say the limit does not exist. And as inspiration, or maybe just as a recap, maybe as a solidification of the idea, a few of you guys, oh, that's no fun. Hold on. For some reason it went missing in like the few moments that I didn't have it up there. All right.
Remember when we could only watch live TV here? Well,
now we can watch live TV here.
in here. Hey, remember running out of DVRs?
Contest.
Is that my sound? Yes, please. Just a small clip. It's not a big one.
Find the limit of this equation.
Calling someone else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And wanting to change George's life definitely didn't make me any happier. All you can do in life is try to solve a problem in front of you. The limit is -1. Oh crap, I lost.
That answer is incorrect. We are in sudden death if this errand can answer this problem correctly. We have a winner.
Limits? I could never remember anything about limits. Limits? That was a big Aaron's haircut. Oh god, it was so cute. Okay, focus, Katie. Focus on the word behind Aaron's head. If the limit never approaches anything, the limit does not exist.
The limit does not exist.
Our new state champions, the North Shore Manly.
Yeah, that was this one. Alright, I want you guys to see if you can graph this function in your calculator and see whether or not you agree. Ready, set, go.
Probably doesn't.
ln of 1 minus x minus sine of x. ln of... Okay, that's good.
Yeah, I can't see them.
Oh, calm down.
Are you guys?
There we go. Now I can see it too clearly.
You can see too clearly now? The rain is gone.
Holy cow, that's
ln of 1 minus x minus sine of x all over 1 minus cosine squared. Wait, how do you do cosine squared in your calculator? It doesn't let you.
cosine. 1 minus
Cosine squared. Put a big old... You could just make it sine squared, but you still have to figure out the squared part. Don't get tricked by the trig notation. Do a big old parenthesis, cosine, and the cosine, then square. It should be fine. They're just one.
Error data type.
What? You didn't type it in right.
Yeah, I guess not.
What's the function look like? Now, the real question is, did she actually solve that function, or did she literally just remember sometimes the limit might not exist?
Well,
I don't think she actually looked at the problem.
Yeah, I don't think she actually solved it either, because the only way to actually solve it or visualize that graph is with calculus BC, and I'm pretty sure she wasn't in Calc BC. She was in AB from what I could tell as to what they covered that year. But that's okay, even though...
so what you're saying is the movie directors suck.
Wait,
I'm just saying the point was that girls can do math, and I'm not sure that proved it. It just proved that girls remember boys' hair and a limit on a board in one class. She says she's 12?
She did look 12.
She did look
Anyway, wait. I'm a little skeptical about the movie. At this part. Well, and a few other parts too. Mean Girls. Have you guys not seen Mean Girls? It's not that old.
I don't watch.
I mean, as in.
I'm a nerd. I watch comics.
Oh, that's true. You're just probably.
Are you swearing again?
Okay, check out what I'm doing.
She was 18.
Check out what I'm doing. You were on your phone checking her age. Put your phone away.
Sorry.
Cosine of x. See it? I put it in parentheses and then do the square. Don't get tricked by the trig notation. Square the whole cosine.
I mean, that's what I did. It's just
Guys, I just showed it and I explained it for the third time.
arrow dated.
Okay, now you probably need to be in radian? Yeah, radian should work. And the limit as x approaches 0. We need to get towards 0. Still need to get towards 0.
So then it just says error.
Ah, do you guys see why? Check out at 0, right? If I was to zoom the window in a little bit and only have the x mins go to like -2 or something, and then have the x maxes go to 2 and then graph, what's going on as I come towards 0? Who cares what's going on the outer extremities? Just look towards 0. And as I come from below, what's the limit? As I come from below, where's my function headed? Positive infinity. And as I come from above, where's my function headed? Negative infinity. Do those limits agree? No. And so according to our notes from yesterday, if anybody was gone, if approaching from either side yields different results, whether they are two different constants, two different set heights, like in letter A, or whether they are infinitely opposite, infinitely in disagreement, like this one down here, the limit does not exist if the one-sided limits do not agree. Now, this one, air quotes around DNE. But since it's an agreement, since both sides are in agreement, we still state the answer and say it's going to infinity. But we cannot with an example like this because they are in disagreement. If the one-sided limits do not agree, the limit does not what? Exist. Hopefully we can understand why and not just something out of boy's hair or a movie. So, let's keep going. What if we were to... This page looks gross. Now, guys, hold on, pause. I don't want you to write down any of those. I want to show you how they work. Maybe we'll write them down next year if you decide to take calc. But for right now, let's just do a few problems and say, hey, can we figure it out? Basically, the properties tell us if we don't know a function, if we don't know its graph, but we do know a limit value of separate functions, we can use those limits as long as x is approaching the same constant. We can use those limits in different combinations or different operations with the functions. Technically, probably need to talk about continuity and stuff like that. We're not going to get super picky. We're just going to say, if we know the limits, even though we don't know the equations, even though we don't know the functions, I do want you writing this down. You just didn't have to write the table down. Skip the whole table. You don't have to memorize it. You don't have to regurgitate it. You don't have to repeat it. You can look in the book, add it if you would like. I just want to see if you can use it. If you know the limit as x approaches c of f of x is 3, limit as x approaches the same constant of g of x is 6, we can use that limit in order to solve when something else gets introduced, like a multiplication or an addition or a square root or a division, as long as the limit exists. So in letter A, the property basically says, think of the limit as x approaches c of g of x, but now just multiply it by -2. So, letter A, just going to start you off, would equal -2 times the limit as x approaches c of g of x, which is 6. So my final answer would just be, no big deal, -12. We don't always need to know the function or its graph or its table in order to be able to solve. Sometimes we could just be given its limit and then plug and chug. So what do you guys think I'm going to do for letter B? Yeah, plug and chug. So the limit is going to equal, if I have f plus g, I can say the limit of f plus the limit of g according to properties. So what can I say the limit is? 9, because it's 3 plus 6. The limit of f plus the limit of g. And letter C, what if I was taking the limit as x approaches c of f over g? If you guys want, I can show you what I'm talking about when I talk about the properties. There is a quotient property that says in order to solve this limit, I can take L and I can take K and just divide them, given I know the limit of F is L and the limit of G is K. We don't have to write that limit, we don't have to memorize that limit, but can we use that limit? The limit as x approaches C of F over G, what would it be? Yeah, 3 over 6, which does reduce to be what? 1/2. Last but not least, what do you guys think for letter D? Good. Final answer, root 3. How come? Because I plug in 3. Huh? Oh. So using the properties, it's not super complicated, it's not super intense, and that's why I don't want you guys to take all the time and write down a table and try to memorize them. And it's kind of more logical, but training your logic, saying, hey, this is legal, this is okay, I am allowed to just go ahead and plug in. Once again, in the table, there is something at the top. B and C have to be real numbers, N has to be a positive integer, F and G, oh, they're just functions, don't have to be continuous. So there are a few conditions that need to be true, but we're just kind of scratching the surface of how to use these properties, and they're not really bad, meaning even if you don't know a function, even if you don't see a graph or a table, if they give you little clues about different particular pieces of the limits, you can use those in solving. I'm going to move this up because it's awkwardly like just kind of chilling down way below. There we go. Let's keep going. There is one other thing that we need to talk about. And Tyler actually brought this up before the Mean Girls clip. Direct substitution. For well-behaved functions. An example of a non-well-behaved function is like that funky one that we graphed yesterday. It was sine of 1 over x, I think, right? You kept zooming and zooming and zooming. It looked like a barcode, and it was like, I have no idea what's going on. That's not a well-behaved function. It is, just not around 0. Not where the barcode was. For well-behaved functions. Functions with vertical asymptotes aren't well-behaved at the vertical asymptote, but they're fine everywhere else. Piecewise functions, they're not necessarily well-behaved at that in-between point, like that one we just graphed and there was that jump. It's okay everywhere else, but the in-between point, the separator x, causes us some trouble sometimes. Well-behaved functions. Polynomials are well-behaved. Let's see, what else can I say is well-behaved? We'll say basically non-piecewise functions and I'm going to say non-piecewise functions everywhere in their domain. And that includes everybody. That includes square root functions and rational functions, which have denominators. That includes logarithmic and exponential. That includes polynomials. Non-piecewise functions are well-behaved everywhere where they exist, everywhere in their domain. It's not going to be well-behaved at a hole. It's not going to be well-behaved necessarily at a vertical asymptote or at a jump. But otherwise, besides those places, non-piecewises are good. Piecewises are also good. Piecewise functions are also well-behaved everywhere in their domain also, because they might have, like, I don't know, holes or vertical asymptotes you have to watch out for as well. But piecewise functions are well-behaved everywhere in their domain, but check the separator. Now guys, I actually talked about the separator earlier this year when we were graphing piecewise functions, but let me just show you a quick example, if that's okay, of what I mean by the separator. If I were to give you f of x is equal to, let me just make up something random. We'll do ln of x for x greater than 0, and we'll do x squared minus 1 for x less than or equal to 0. What is the separator that I'm talking about in this example? Yeah. So when I'm saying separator, what I'm referring to is that x value that separates that is in both of the inequalities. Does that kind of make sense? It is the x at which we separate. It is the x at which, okay, there's one piece. Okay, wait, hold on. Now it's time for the other piece. It's where the two pieces come together, if that's a better way of saying it. I call it a separator because it breaks up the domain. Like on a number line, it would be the point at which on one side is one function, on the other side is the other. But when I'm talking about separators, I'm talking about the function, not the function, the x value that cuts up the domain. Okay, anyway, but all of that to say, I was just describing what well-behaved means. That was the very beginning. After I say for well-behaved functions, what does this box say to do to solve for a limit? Plug in? What? But we just talked about, and we spent a long time yesterday about it doesn't really matter what's going on at a point. It's what the approach is showing. But for well-behaved functions, what's at the point is where it's approaching. For well-behaved functions, what's at the point is where it's approaching. So it's the same thing. It's a shortcut. So let's go ahead and, if you guys think about it, we've done like 2.5 days on limits right now. We've done a few examples, but not a lot. Let me go back to a few of the ones that we've done and that we've thought about. In this one, let's see. Here we go. In this one, the limit as x approaches 2 of 3x minus 2. I actually didn't show you guys this page earlier because I didn't quite want to. We did see a table, and we did see how the table showed us from below and from above that the function was approaching what? 4. Good. The limit was 4. So we could say L was equal to 4. The limit was equal to 4. But guys, if you look at this graph, it's a well-behaved function. It's just a line. If you look at the beginning, 3x minus 2, there's no discontinuities. There's no piecewise function. There's no denominator or square root or ln or weird tangent that has a vertical asymptote. It's a well-behaved function. So the well-behaved functions, as you come from below and from above a point, where it's approaching is what's actually filled in. Now, once again, a limit technically isn't concerned with what's at a point, but for well-behaved functions, where the limit is, the height that I am approaching is actually there, and it can be a shortcut. So a shortcut for solving this one is, guys, look at this one. If 3x minus 2 is well-behaved, the direct substitution that you just wrote down said, well, if it's well-behaved, instead of doing this whole table graph thing, what can I do instead? Plug it in, plug it in. Plug in 2 and say 3 times 2 is 6, and 6 minus 2 is, it's going to work every time you're working with a well-behaved function. Now, why do you do the whole graph thing, the whole table thing? And number 1, you might not always see a function. And number 2, they're not always well-behaved. Let's go ahead and, you guys understand that. You're not always well-behaved. Anyway, and theoretically, you've grown up a little bit since you were 2.
That hurts my feelings.
So, coming back, well, it's honesty. I'd say I'm not always well-behaved either. It's called human depravity. That's why we need grace. Hey, the gospel in now. So, oh my goodness, we have 6 problems. It takes us forever to solve a limit, unless they're well-behaved. And unless it says we're allowed to use direct substitution, which homework you're allowed to do, I think, towards the end. So wait a minute. How am I going to solve 6 limits in 6 minutes when it's taking us 2.5 days to do like 5 problems? Not really. We just plug it in. A parabola in letter A. A parabola is well-behaved. Hold on, guys. These are the best problems in the whole section. A parabola is well-behaved. Meaning, in order to solve this, don't graph it, don't do a table, just see what x is approaching and what are you going to do with them? Plug it in, plug it in. Really? Yeah, the limit is 16. What's going to happen when you go to your table and approach? You're approaching 16. What happens when you go to a graph and you look at it? It's approaching a height of 16. Oh, plugging in is shorter. Exactly. Letter B. Is 5x well behaved? Yeah. No denominator. 4 is in the domain. So all we got to do is say 5 times 4 is... Dun, 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 dun. Hey, we've solved 2. It's been less than a minute. Letter C. Oh no. Tangent has vertical asymptotes. X is in the denominator. It's not well behaved, but is it well behaved at pi?
Yeah.
Pi's not 0, so my denominator's okay. And tangent of pi, it might be a little hard for some of you guys, but if I go to pi, and if I think about my cosine and my sine, I end up with 0 over negative 1 all over pi. And 0 over negative 1 is just 0. Guys, this is well behaved at pi. There's no vertical asymptote here. There's no number over 0 here. So 0 over anything is just... So even though this entire function is not always well behaved, he's doing fine at pi. Plug him in, done. How about letter D? Easy. Why? Square root? Negative numbers are bad, but what about 9? 9's fine. Plug it in. Square root of 9 is 3. For letter E, cosine doesn't have any vertical asymptotes. That's good. So I can just plug in pi, and I can plug in pi to cosine and plug in pi, well, to x, wherever it shows up. Cosine of pi, some of you guys have already done it. I do have it up above here in the point. That's negative 1, and negative 1 times pi is just negative pi. Letter F, that's a parabola, no big deal. He's well behaved. There's no square roots, ln's, trig. There's no vertical asymptotes. There's no piecewise function. Plug it in. How you guys liking direct substitution? So suffer through the table, suffer through the graph. It's giving you the idea of the limit and the importance of approaching. But you get to direct substitution, which is grand, which is great, which is spectacular. Except, hey look, do your homework tonight. Except, oh my goodness, when it's not. What? I know we're not going to get very far, but pause. We still like 3 minutes. What are you doing? Oh, because you're starting. I thought like he was just leaving. I'm like, okay.
You know, I wouldn't be surprised, but
Coming back to our notes. Direct substitution. Guys, look, we ended there in 12.1 and we begin there in 12.2. We like direct substitution. It's always great until it's not.
so then
It works until it doesn't.
Let's
There you
never
go.
get to the point where it's not.
So what happens if it doesn't work?
Give up.
No.
No?
We're Americans, do things.
You should be writing. So, finding limits algebraically. We've done graphically, we've done numerically, and we've just scratched the surface on algebraically saying, hey, try to plug in. If it's well behaved and it works, you're done. That's step 1. Finding a limit analytically, algebraically, same thing. Plug it in. If it works and it's well behaved, you're done. The problem is about number 2. Right here, in between 1 and 2, I'm going to put the note, what if, I'm not even going to say what if, I'll just say if plugging in doesn't work. Now hold on, why would plugging in not work? When or what happens if you plug in and you don't get an answer? What could happen that an answer wouldn't exist?
I guess there could be
Divide by 0.
Could be a vertical asymptote, a division by 0. Now, there are 2 different ways of dividing by 0. If, and I'm going to kind of put a little category here. If plugging in gets you 0 over 0. Now, there are technically 2 ways of getting over 0. Either 0 over 0 or a number over 0. And the answers are very, 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 very different. But if you get 0 over 0, most of you would say, DNE, the limit does not exist, I'm done. The problem is, no. If you get 0 over 0, and I'm not kidding about this, and I'm going to be strict about it, and I'm going to actually take off points, I want you guys to write, keep going. If you're solving a limit and you get 0 over 0, that is not a sign that the answer does not exist. It's a sign that the function does not exist, but the limit says, I don't care about what's there anyway, necessarily. So the approach could still agree even if the function doesn't exist. Now, if you guys are like, I have to write 9 letters and an exclamation point, okay, you can write kg if you want, not kilograms. You can write kg if you want. But if you ever plug in and get 0 over 0, I want you to think, keep going. The question is how, and that's what we're going to have to wait until tomorrow to see. It's going to involve maybe factoring, maybe simplifying a complex fraction, maybe multiplying by conjugate. Basically just kind of doing some math to try to change things up and see if it makes all the difference. Tonight, what's your goal? Finish 12.1. Tomorrow I'm going to, well, aim to have my computer working. Not that that's totally up to me. So that we can start right away and not get behind. But you guys still did a great job. Made it through 12.1. We got to get going in 12.2 tomorrow.
We are behind.
Do your homework. Yes, we're like half a day behind. Do your homework as best you can, and I'll quickly answer questions. But then we're busting into 12.2. Bye, guys. Well, that was good timing. Didn't even plan it.
Bye, guys. Boo.
Hug a Calc kid today, especially a Calc and French kid. They have a rough day.